We're going to continue our look at the solids of revolution by looking at slightly more complicated regions. And the regions that we are going to look at are ones that are very similar to what we did with the area problem. How we extended the area problem, we're essentially going to extend the volume problem as well. So the one specifically that we will look at in this video involves regions that look like this, right? And again, the three-dimensional nature of these problems make it more difficult to sketch. So I will describe what we have. So now let's say we have two functions, y equals f of x and y equals g of x. And we now define the region between those two curves. Right? And suppose we take that region and revolve it around the x-axis, right? So what will happen is we will get a solid that has a hole in the middle, right? Since there's no region right here, we're saying the region starts at our upper function and then ends at the lower function. When this region is revolved, we're going to get a hole in the middle. In fact, let me over here kind of sketch what one of the disks would look like in our Riemann approximation. And again, I will set it flat. So essentially what you will have is you'll have an outer border and then you'll have an inner border. That part would be solid all the way through, and then you'd have a hole in the middle, right? So that's what the disks would look like in this case. Again, I slice it this way, and then I turn it flat, just kind of lay it flat. So this type of solid is called a washer because it has a hole in the middle, right? And the question is, what is the volume of this entire solid that's generated when we do this kind of revolution? Well, all we have to do is use the same principle that we did for area, but now apply our disk method, right? So for instance, pretend for a second that the region goes all the way down to the x-axis. What if I were to revolve that region around the x-axis, I would use this definite integral. So from a to b, and then I would have pi times my function squared dx, right? And here the lower limit is a and the upper limit is b. But now, in order to get that hole in the middle, I would have to find the volume that's bounded of the solid that's bounded by G and subtract it. So take away what I would get if I revolved the red region around the x-axis. So then it will be minus, and then I would have the same limits, but now it will be pi times g of x squared dx, right? And this is actually called the washer formula. Normally how it's written, it's written as a single definite integral, and how you get that definite integral is by using our properties of definite integral. So I can combine these two into one, so it's the integral from a to b of pi. And then what I have is the difference between f of x squared and g of x squared. And then integrate with respect to x. So this is our volume by washers. And this is used when we have a region that doesn't go all the way down to the x-axis. It's bounded by two curves, and then we're revolving around the x-axis. So this is our washer formula. right? And then something similar can be done for functions where we have x in terms of y, right? So let me sketch that one. Right, so let's say we have two functions, one graph that looks like this, another one that looks like this. And remember, they could meet at the endpoints, but the same assumptions that we made for area, we're going to make for volume, that at most they can touch, but the curves won't cross, right? And again, I'll use the same notation that we did there with C and D as the limits on the y-axis. And then let's say the larger x values are defined by w of y, and then the smaller one, v of y. So now my region, right, is between these two curves. And if we're revolving around the y-axis, right, then again, here's the process. We would take the volume of the larger solid, so up to the w from the w function all the way across to the y-axis, and apply our disk formula. So it's pi times w of y squared dy. But then since I don't want the region between v and the y-axis to be revolved, right? I don't, because there's no region there, I'll have to subtract that volume. So, not A to B, C to D. So we have C to D, C to D, and then we have pi times v of y squared dy. So this is how it's set up separately, but it's often more efficient if we, again, use the same property of the definite integral that we used up here and combined it into a single one. So they both have a pi in common, so I'll kind of factor out the pi, and then it's the function on the right squared minus the function on the left squared. Right? And again, this is our washer formula, but this is where everything is in terms of y. The limits are on the y-axis, the function is in terms of y, and we're revolving around the y. All right? So it's just a slight extension, right? And let's do a couple examples seeing how this works. All right, so examples. All right, so let's do one where we take the region that is bounded. So suppose the region enclosed by the line y equals x and the parabola y equals x squared, let's say in the first quadrant, is revolved about the x-axis. Right? What is the volume of the solid formed? Right, so what is the volume of the solid formed? Right? And you can tell many times when, anytime the region is now between two curves or a line and a curve, there's always going to be a difference in your calculation, right? And in this case, our first formula applies because let's see, our functions both are in terms of x. The revolution is about the x-axis, and we don't have the limits, but we can find the limits because again they're saying that the region is enclosed by this line and this parabola. So that means the limits will be defined by where the line intersects with the parabola. So let's start with a sketch to get a sense of what this, at least the region, what it might look like. Alright, so here's our line, y equals x. And then we know our parabola is like this. And then it goes up like that. So this is y equals x squared. So here is our region. And for this one, since everything is in terms of x, you notice how I shade the region with these vertical stripes. Again, and the upper limit there, that's going to be my f of x, my larger function. When I say upper limit, meaning the upper function or the upper boundary. And then the lower boundary is going to be the parabola. That's my g of x. So now what we have to do is figure out where they intersect. Now, the algebra for this isn't very difficult. In fact, you might be able to tell just by looking at these simple functions what x values will be the same whether I square them or I just keep the x value, right? So what numbers are the same when I square them, right? Have you figured it out yet? Well, if not, let's see what the algebra says. So we will take our x squared, set it equal to x. Again, whenever you're solving equations like this, it's best to think of factoring. That way you don't lose any solutions. So if I move everything to one side, factor out an x, I have two solutions. X is equal to 0, and that's what we would expect right there. And the other one is x equals 1, and that's what we would expect right there. So those are our limits. So now, because it's a volume problem, right? It's not just area, but it's now a volume, we're going to apply our washer formula. So using the washer method, right, our volume is this. So it's going to be an integral from 0 to 1. And then we have our pi, and it's times the quantity, the upper function, right? X, we have to square that function, and then minus the lower function squared. So it's x squared squared, and that's with respect to x, right? So that's the setup. And then let's simplify the second term by using our properties of exponent. So we have 0 to 1. We can take the pi outside, and then inside we're left with x squared, and then minus x to the fourth dx. So both power functions. So we have pi times. Now let's find our antiderivative. So we have 1/3 x cubed minus 1/5 x to the fifth, and then that's from 0 to 1. Alright, so now at the lower limit we know that both terms will be 0, so that simplifies our work quite a bit, and all we have left is, so at the upper limit we have 1/3 minus 1/5, and then at the lower limit we have 0 minus 0. So it's pi times 1/3 minus 1/5. We can get a common denominator of 15 there. So this is 5/15 minus 3/15 for 2/15. So our volume is 2 pi over 15 units cubed. And so many of the answers to problems that you see in the sections on volume are always some multiple or some fraction of pi, right? So pretty straightforward. Let's do another example. Now this one, what I will do, I'm going to give you one, so let's do this. So I'll just sketch this and give you all the information you need. It's going to be a very simple function. It's going to be a simple square root function, and the limits will be from 0 to 4. Right? And the region is between the x-axis and our square root function. So it's this region, right? Or we can think of it this way, right? And the reason why I'm shading it two different ways is because this question is going to have two parts. One part will be what is the volume of the solid formed if we revolve it around the x. So there. And then what's the volume of the solid formed if we revolve it around the y, right? So for part for part A, let's solve it if the revolution is about the x-axis. Now, if it's about the x-axis, because the region goes entirely down to the x-axis, this is our disk method. If I revolve this portion, right, that's under this curve around the x, there is no hole in the middle, right? So if the revolution is about the x-axis, then the disk method applies. There is no hole, right? Because the region goes all the way down and it touches the axis of revolution, right? So let's solve the part A. So our volume, right? So let's finish this. So the disk method applies. So then the volume in this case will be the integral from 0 to 4, and it will be pi times our function squared. So it's the square root of x squared. Well, you square the square root, the root goes away, and the square goes away, right? They're inverse functions, so they cancel each other out. So we're left with x, right? Not quite as easy as integrating just a pure constant, but still pretty easy. So we're going to have pi times 1/2 x squared evaluated at 0 and at 4. So at 4 we'll have 16 times 1/2, so that's 8. So we will have 8 pi at the upper limit, and then at the lower limit we'll have 0, right? So the volume of the solid formed, if we take that region, revolve it around the x-axis, we will get 8 pi units cubed. What if we revolved around the y-axis, right? So part B. So if the revolution is about the y-axis, then think about it. See, because if we're revolving around the y-axis, right here, in fact, let me mark this off. All this empty space will create a hole in the middle of this solid, right? Because there's no region here. It's the same region. I'm just revolving it about the different axis. So if I now change my perspective and think in terms of the region between this line and this curve, then I have to apply the washer method. Again, because the entire region doesn't go entirely down to the axis of revolution, or in this case, across to the axis of revolution. So the washer method applies. Not only that, but we are also going to have to modify what we're thinking, because in order to use the washer method for a revolution about the y, we need to convert everything over in terms of y. In other words, I need to know what the limits are. I need this function to be x equals a function of y, and I need to know the equation of that line. Right? So let's do that, and I'll write the y information in green. Now, when x is equal to 0, y is still equal to 0. So this is still the lower limit. So I'll put, maybe I'll just do it there like that. It's still 0. But the upper limit now, I'd have to figure out the value of y when x is equal to 4. So if I plug this value of 4 into my square root function, I'll get a y value of 2. So this now, my c, my lower limit is 0, and my d, my upper limit is 2. Right? Now, I need to write this in the form x equals a function of y. So if I solve this equation for x, I will get x equals y squared. That's the equation of the curve. And the equation of that vertical line, right? So this line is the x equals 4 line, right? Vertical lines are always of the form x equals some constant, right? So this is my function on the right, and the curve is my function on the left, all right? So let's write down what that definite integral will be now, because I'm not changing the region. The only thing I'm changing is my axis of revolution. So I just have to express everything now in terms of y. So as we said, our limits are now 0 to 2, and then I'll have pi. And now I have to take the, in this case, function on the right, which is the vertical axis, right, or vertical line, x equals 4. So it's a constant. So it's going to be 4 squared, and then minus the equation for the curve squared. Well, that equation in terms of y is y squared. So this will be y squared squared, and I integrate that with respect to y. Right? So in other words, this vertical line gives me like the outer radius, right? The one that's further away from the axis of revolution. And then this part of my square root, or also my parabola function, gives me the inner radius. It's the boundary that's closest to the axis of revolution, right? And then taking that difference of the squared functions will give me that the volume of the solid that I need, right? So let's factor out the pi, and then it's the integral. Oh, wait, no, let's not try to squeeze that there. Let me scroll down. So take out the pi. We have the integral from 0 to 2. And then what are we left with? Well, we have 16 minus y to the 4th dy. And then let's, so we bring down the pi. Let's find our antiderivative. So it's going to be 16y minus 1/5 y to the 5th, and that's from 0 to 2. So again, having a lower limit of 0 will help in our evaluation. At the upper limit, we'll have 16 times 2, so that's 32, minus 1/5 times 2 to the 5th, that's again 32, and then at the lower limit, both terms are 0. So minus 0, minus 0, right? And then what we have left to do is to take 32. Now let's write both of these with a common denominator of 5. So this is 160 over 5 minus 32 over 5. And then that's, so 160 minus 32 is 128. So I'm left with 128 pi over 5 units cubed, right? So it's different. We can look at these two volumes and realize that yes, the volume that we get by revolving around one axis is not necessarily the same as revolving around the other axis. Now, depending on the type of curve and what your limits are, maybe you could have like a really symmetrical type of a situation where it doesn't matter if you integrate or if you revolve around the x-axis versus revolving around the y. But in general, it's hard to know when the solids are going to be completely symmetrical, right? Because they're so hard to visualize. So even though we can use our formulas, as long as we recognize when the different formulas apply, we can do this without actually seeing the solid. It's not until we actually compute the numbers that we can compare to say, hey, the volumes are the same, or in this case, the volumes are different, right? But the washer method, again, is just one slight generalization of the disk method, and it's when your region now doesn't go entirely down or across to the axis of revolution, but it's stuck between two curves, right? And next up, we have more generalizations of the volume problem. See you then.